Hello guys, good evening.
Hello, sir.
Yeah. Okay, just check what have we done last class. Okay, just 1 minute, we'll start. Okay. Do you have any exam going on in the school?
Yes, sir. We have the semesters.
It's going on.
Yes, sir.
Chemistry, it is done or you have to write?
The next exam is good.
Next.
Yeah.
What is the portion?
So full organic, I think.
Full organic.
Yeah, and solid state and coordination
Okay.
and all this. And DNF block.
D and F block is also there.
So DNP.
Okay. So last class we had discussed Okay, so last class we had discussed about the various types of unit cell. Okay, FCC, BCC, HCP also we have discussed, and we have also discussed the arrangement of atoms like ABC, AB type arrangement we had discussed. Location of void also we have done. So today we are going to see the ionic crystals. This part actually you have to memorize, because the position of cations and anions you have to keep in mind, because based on this only they frame questions in the exam. So understanding is not very much required over here. If you know the position, suppose NaCl, the example I'm considering, if you know the position of Na plus and Cl minus in NaCl crystal, based on that you can do all the questions. Okay, so here you have to just memorize the position of cations and anions. I want to show you some questions here. Sec. Okay, try this question first. This one. Done? Okay. No, it's not that here. No, it's not that also, Ruchir. Yeah, Ruchir, you got it right. Ruchir Singh, you got it right. Ruchir Parekh, that is not correct. See, this question, why I've given you here, that the kind of question that they ask here, you should know the position of these voids, and that we had discussed already last class. Yeah, that's correct, Pradyut. Yeah. See, answer is C here, AB. Okay. Let's see, I'll do this. A compound is made up of particles A and B. A forms FCC packing. Okay. So when it says FCC packing, it means A is forming FCC packing, or they can also say CCP, both are same thing. Okay. FCC or CCP packing, it means this A is present at corners and plus face center. Corner plus face center. B occupies all octahedral void. So B is present in octahedral void, and we know the position of octahedral voids, that is there at the body center plus at the edge center. Okay, so you imagine the cube where the body center we have B and edge center we have B again. If all the particles along the plane as shown in figure below are removed. Now this plane, you see how this plane looks like. This looks like, you see the room in which you are sitting in. You see any top edge you take, any one top edge, and you come, you consider a plane which passes through that edge, and it comes diagonally opposite to the another plane, another edge, opposite side. So from the top to bottom, diagonally you have to come, like the edge that you have. Means what? You consider this edge and draw a plane like this along this edge. So this plane, you see, this plane obviously it passes through the two cornered atoms here, and these are the face centered atom. Yes or no? Of this face and this face. And along with this face center, it also passes through the body center. Yes or no?
Yes.
Correct? So if you imagine that plane from the top edge to the diagonally opposite edge, the plane that is coming down, okay, this plane is passing through the body center, right? And the two face center, two cornered atoms we have here, 2 + 2, 4 cornered atom here. So could you tell me how many A atoms have been removed? How many A atoms have been removed?
1.5.
4 cornered A and 2 face centered A have been removed, right? So out of 6 face center, 2 have been removed. So the contribution of A, if you see here, that would be 2 face center have been removed. So 4 into 1/2. And 4 cornered atoms have been removed. So 4 into 1/8. Is it correct?
Yes.
So it is
So
2.5. 3/2, is it? Sorry, 2.5 means 5/2. Correct? If you talk about B here,
So what do we 2 into half?
Huh?
So it should be 2, right? Only 2.
Sorry,
face
come
centers.
again, yeah.
Only 2 face centers, right?
Yeah, 2 face center have been removed.
So but you wrote 4 into half.
Your voice is,
it should be only 2 into half, only 2
no,
face.
no, 2 into half has been removed. I am considering the contribution.
Okay, okay.
I'm considering what you do, you can consider 2 into half and then you can subtract, right? I'm directly considering here the contribution of A in the unit cell.
Okay.
So out of 6 face centered A atom, 2 has been removed. So we are left with only 4 face centered and 4 corners. Is it fine now?
Yes, sir. Yes.
Right? So 5 by 2 is the contribution of A in the unit cell. Similarly, the contribution of B is what? 2 edge center has been removed and 1 body center. Means 3 B has been removed, right? So out of 12 edges, right? Out of 12 edges, 2 edge center has been removed. So 10 is left. Contribution of edge center is 1 by 4. That is it. Because body center has also been removed. So it is what? It is again 5 by 2, you see we are getting. So the formula is what? Formula is AB. Understood? Clear? So this is the easier way, I think. I usually do like this only. I just count the contribution of atoms in the unit cell and the ratio finally. Otherwise, you can also count whatever the contribution we had initially, and after removal, like what part you have been removed, subtract that, you'll get the answer in that way also. But this way you can do it in one single step. Is it clear? Right? So question is not difficult. Why I have given you this question? So that you can understand that how they use the concept of voids here. If you do not know that the voids are placed at the edge center, you won't be able to do this question. Understood? I'll show you 2 more questions here. I don't want you to solve now. We'll do this question a bit later, but just see these 2 questions. This one we have done. You see this one question. Don't try this. We'll discuss a bit later. You see here in this question, what is given? In a solid having rock salt type structure. Now the question is, if you do not know what is rock salt structure, you are not able to do this question, right? Rock salt structure, if all the atoms touching the body diagonal plane are removed. So first of all, you should know the rock salt structure, then only you can do this question. So for that, we are going to discuss the different types of structure we have. Okay, one more question you see here. We'll do this question a bit later. Okay, just now you let it be this one. This question you see. It is also based upon the structure of CsCl. And that's why I said that you just need to memorize this. If you do not memorize this, logically you cannot do this. CsCl has BC arrangement. You know what is BC arrangement? Corner plus body center. But if you do not know at body center what atoms are present and at corners what atoms are present, you won't be able to do this question again. Okay, so all these questions depends upon the structure. Okay, so you should know all these structures. So ionic structures, ionic crystals, we had discussed, we have started last class, and I've given you the radius ratio for triangular void. Okay, with the help of what I said, the geometry, you can find out the radius ratio for different for different voids also, like tetrahedral we have octahedral void, we have cubical void, all these things you can find out. But I'm giving you the data because derivation they have never asked. Okay, so you should know the relation here. So write down this table, you draw all of you. I'll give you the entire thing here in this table. 2, 3, 4. Okay, just a second. This is the radius ratio. And then we have coordination number. Arrangement. Of anions around cations. And we have some example for this. Okay, so the radius ratio is 0.155 to 0.225. Radius ratio means radius of cation divided by the radius of anion, which we can also write it as RC. C stands for cation, RA, A stands for anion. If this falls in this range, then the coordination number is 3, and the arrangement of anions around the cations are triangular, which we also call it as planar triangular. And we get triangular void here. B2O3 is an example. Example is not important in this. If the radius ratio falls in this range, so one more, we have to consider one more. Okay, 0.2252 to 0.414. Coordination number is 4. Arrangement is tetrahedral. Example is this zinc sulfide. If it is from 0.4142 to 0.732, coordination number is 6. Arrangement is octahedral. These two are the important one, tetrahedral and octahedral. NaCl, example. If it is from 0.732 to 1, coordination number 8, it is cubic, that is body centered, and it is CsCl, the example we have. So this radius ratio just you have to keep in mind here. Copy this down. The lower limit you must take care of. To solve the question, you can equate the lower limit to solve the question. Means you can equate this to radius ratio should be equals to 0.225, should equals to 0.414 you can take. So lower limit you can equate in all these range. Did you finish it? Okay, now the structure of crystals, heading you write down, structure of crystals. See, we are going to understand, we are going to take the reference of 3 types of compound, okay? The first one is the simple ionic compounds, which is AB type, and then we have AB2 type, and next we have A2B type. These 3 types of structure we have. Apart from these 3, we have other structures also that we are going to see, okay? So first write down, the first one, structure of structure of simple ionic compound of AB type, means NaCl type. It is AB type structure. AB type structure, we also call it as rock salt, or NaCl type structure. Rock salt or NaCl type structure. Okay. Example we have for this. We can have oxides and sulfides of group 2 metals, of group 2 except BeS, right? Halides of silver, except AgI have this type of structure. Halides of alkali metals also we can consider. Like we have NaCl, it's there only. LiCl we can consider, right? We can also consider some examples like CaO. All these molecules has NaCl type structure. Okay. Now, what is important here? Point wise, just you write down these. First point you write down in this, that all, I'm taking the reference of Na plus. Okay, if the statement which I'm giving you for Na plus, this will be true for all cations in these structures, right? So write down all Na plus ions. It's surrounded by surrounded by 6 Cl minus ions, and each Cl minus is also surrounded by surrounded by 6 Na plus ions, right? 6 Na plus ion. That's why the coordination number you see for each ion, it is 6 over here. Right? Write down the coordination number of each ion is 6 over here. Coordination number is 6, and hence this type of crystal we also call it as 6:6 arrangement. Important. This question also they ask in the exam. What kind of arrangements is there? 6:6 arrangement. Okay. So first we'll take the the coordination number of cation. Here we write first, and then we'll write the coordination number of anion. 6:6 arrangement we have. Next point. Cl minus ion forms forms CCP lattice. What do you mean by CCP lattice? Face center plus corner. Okay, forms CCP lattice in which all octahedral void is occupied by Na plus ion. Okay, CCP lattice in which all octahedral void is occupied by Na plus ion. I want you to tell me the number of Cl minus present in the crystal, 1 unit cell. Number of Cl minus and number of Na plus. Number of Cl minus and the number of Na plus, because you know the position of Cl minus and Na plus. Hence, you can easily count the number of Cl minus and Na plus. Is it 4? Yeah. So Cl minus form CCP lattice, means at corners, so 8 into 1 by 8 plus face center, 6 into half. So we have 4 Cl minus present, Na plus 1 at the body center, right? Since octahedral void, and 12 H center we have, 1 by 4 is a contribution, so it is 4. Since Na plus and Cl minus we have equal in number, that's why the molecular formula is NaCl, and hence the structure is, right? Should be equal. Then only it satisfies the crystal. Okay, that's one thing. Now, if you look at the position of all these ions, so what we can write, suppose all these are Cl minus, right? It is present here, diagonally opposite. This is Cl minus. Okay, and here also we have 2 Cl minus. I'm just drawing one phase here. Oh, 1 second. This is the face of the unit cell, right? All these are H center, right? So here we have Na plus ion present, cations. Here we have Na plus ion present, cations. Here also we have Na plus ion present. And here also we have Na plus ion present. Okay, so if you look at this distance, this is the edge length. Right? So edge length is A. So if I ask you to write down A in terms of radius, what would you write? A is equals to, we can write 2r plus the radius of cation, this distance, plus 2r minus the radius of anion, which is this distance. Yes. So the radius of cation plus the radius of anion, r plus plus r minus, is equals to A by 2, right? Okay. If I ask you A in terms of the radius of anion, you can think of this distance. This is the phase diagonal, yes or no? This is the phase diagonal. So we can write 4r minus is equals to root under 2a. Okay, so a we know in terms of r minus, and hence any one thing if you know out of this three, r plus r minus a, you can find out all the three here with this relation. Clear? No doubt? Yes, tell me. Correct? Now, if you have to find out the packing fraction of the crystal, right? Method is exactly same. You need to find out the volume occupied by the atom. Here we don't have atom, but we have ions. So volume occupied by the ions divided by the volume of the unit cell. Okay. Usually they don't ask this question, to find out the packing fraction, but you should know the method how to do it. Okay, it's not that tough. I'll just do it for this one. For all other crystals, we are not going to discuss this thing again. Okay, because it is not that important. But you never know, it's there in the portion. So what they're going to do in the exam, you never know. So how to find out the packing fraction of the crystal of NaCl here? So again, the packing fraction would be equals to the volume occupied by Na plus volume occupied by Cl minus, and this whole thing is divided by the volume of the cube, that is A cube. Now we have 4 Na plus, so volume will be 4 into 4 by 3 pi r plus cube plus 4 into 4 by 3 pi r minus cube divided by A cube. R plus R minus, all those relation you have already. I've given you in the previous slide. Okay, based on the data you can find out this thing, right? So expression would be this: 4 into 4 by 3 pi R plus cube plus R minus cube radius of anion divided by A cube. You can solve this, you'll get the packing fraction. Is it clear? Any doubt?
So you wrote an extra R cube.
Sorry? Acha, R I have written extra. This one there.
Then it should be 4 by 3 pi, right? You have written 4 by.
Acha, 4 by pi I have written. Okay. So it is 4 by 3 pi. Okay. A structure, the crystal of NaCl I am not drawing. Okay. You know the position of Na plus and Cl minus. Okay. NCRT, all the structures are given. You can see that easily. You can understand it. Okay. So all the examples of rock salt type structure I have done, they all have this kind of arrangement.
But here, what we get a specific value of R plus and R minus, like in terms of A. We won't get a range, right?
Yeah, we'll get a specific value of that anion because here we have Na plus, no. So Na plus ka R plus value will be fixed. R value will be fixed.
Okay.
Cl minus R value will be fixed. So here, see, the range is what? To what extent the void should be there and the arrangement is tetrahedral or octahedral. Okay, for that we have that range. But here we'll have the certain value, specific value of R plus and R minus.
Okay, sir.
Right. They won't ask you this thing to calculate the packing fraction of ionic crystals. Normally they'll ask in our covalent compounds where the R value is same. So you don't have this R plus and R minus present over there. We have only R, hence the calculation is easy over there that we did last class. Okay, but if they ask, the method is this only. Okay, so this is one type of crystal. We call it as AB type ionic compounds. Example is NaCl. The another one, write down. The second type of crystal we have It is cesium chloride type, CsCl type structure. Write down. Arrangement for these ions are BCC type. BCC arrangement we have. In this CS plus ion present at the body center. And Cl minus at the corners. Okay. Coordination number for each ion, write down. Coordination number for each ion is 8. Ion is 8. Hence, it is called 8:8 arrangement. 8:8 arrangement. The number of CS plus and Cl minus, if you count, it is 1 only. The number of CS plus ion is equals to, it is there in the body center, so 1. The number of Cl minus there at the corner, so 8 into 1 by 8 equals to 1. Hence the formula is CsCl. Okay, since the ions are there at the body center and corners, so along the body diagonal, if you see, the atoms along the body diagonals are in contact. So body diagonal is root 3a, which is equals to 2r plus 2r minus equals to root 3. Example for this type of crystal we have CsBr, CsI, we can have TiCl, TlCl, TlBr, etc. This is another type of crystal here. The third type we have here, copy this down. Third type of crystal, it is zinc blend type, ZNS type. We also call it as sphalerite type structure. ZNS. Write down, it exists in two different forms. It exists in two different forms. The first one is zinc blend A. And the second one is wurtzite structure. Wurtzite structure. Write down. First one, write down zinc blend. It has It has FCC or CCP arrangement. FCC, CCP arrangement. The sulfide ion S2 minus forms CCP arrangement, means corner and the face center, and Zn plus 2 occupy half of the tetrahedral void TVs. Okay, the number of sulfide ion, if you calculate, it is again 4 because it is CCP. For Zn plus 2, half of the tetrahedral void, there are 8 tetrahedral void we have, 2 into n, last class we discussed. Since it occupies half, so this is also 4, and hence the formula is Zns. Done? Okay. Next is each zinc ion is surrounded by surrounded by 4 sulfide ion, 4 S2 minus ion, and vice versa. Means each sulfide ion is also surrounded by 4 zinc ion. Yeah. So here the coordination number is 4 for each ion, and hence it is 4:4 arrangement. All these are informations basically, and this question they ask in the exam. Okay, example for this kind of arrangement. Example is not that important. AgI we have, BES we have this kind of arrangement. Okay, CuI, etc. One note you write down. The bond between zinc and sulfur the bond between the zinc and sulfur has significant covalent character. Right? Like I said, Zn plus 2 present in the half of the tetrahedral void. So it is present in alternate tetrahedral void. Okay. The second type of structure we have in this, that is wurtzite structure. One small difference we have in this second structure of this. Wurtzite structure. Write down, it has HCP arrangement. It has HCP arrangement. So S2 minus, it again adopts HCP arrangement, and Zn plus 2 occupy again here half of TVs, half of tetrahedral voids. Okay, arrangement is 4:4. Here also the arrangement is 4:4. Coordination number is same. Okay, so AB type structure molecule, ionic molecule, has these three types of structure possible. Okay, NaCl type, CsCl type, and this zinc blade wurtzite type structure. Okay. Now, another one is second type of molecules, AB2 type. AB2 type molecules. We also call it as fluorite structure. Okay, fluorite structure, important. This fluorite and antifluorite both are important. Fluorite structure. Write down. Example of this we have, very common and important example. We have AB2 type, so CF2 molecule. We'll see the important points here with respect to this molecule only. Write down for Ca2 plus. Ca2 plus means all cations of this type of structure. This has CCP arrangement first of all. CCP arrangement, and its coordination number is 8. Each Ca plus 2 ions is surrounded by 8 F minus ion. All these informations, they sometimes ask question like this: which statement is correct for this molecule? Okay, so what we can say, each Ca plus 2 ion is surrounded by 8 F minus ions, hence the coordination number is 8. That is what I have written. Okay, number of Ca2 plus, if you count, because it is FCC arrangement, so number of Ca2 plus is again 4. Okay, for F minus, you see F minus ion, it occupies all TVs present in the unit cell. All TVs present in the unit cell. And that's why the number of F minus ion is equals to 8. This is 8, this is 4, and hence the formula is CaF2. Right? For the crystal, the formula is CaF2. Each F minus ion, it's surrounded by 4 Ca plus 2 ions. So coordination number of this is 4. Okay, each Ca plus 2 ion is surrounded by 4 F minus ion, hence the coordination number is 4. Right? What kind of arrangement? We'll write down first cation and then anion. So it is 8:4 type of arrangement. 1 second, guys. Yeah, done. So this is the AB2 type fluorite structure we have. Okay. 1 second, let me just pause this out. This is annoying. 1 second, guys. Okay. Okay, this is fluorite structure AB2 type. One more type of structure we have, which is exactly opposite to the one that we had discussed, that is fluorite. So this one is fluorite. The another structure is A2B type, the third type of structure. Okay, first one, second one, and the third one is A2B type. A2B type. This structure we call it as antifluorite structure. Antifluorite structure. Okay, everything is just opposite. Means you can see here the position of cations there in fluorite here becomes the position of anions and things like that. Okay, so suppose I'm taking one example here of Na2O type. Suppose Na2O, the example I'm taking. So the position of O2 minus ion here, you see, O2 minus ion, it is arranged in CCP manner. CCP arrangement. And each O2 minus ion it's surrounded by four, it's surrounded by, sorry, eight Na plus ion. 8 Na plus ion. The number of O2 minus here, it is again 4. Is 4. For Na plus, you see, Na plus ion present in all tetrahedral void, and each Na plus ion, the coordination number directly I'll write down, for Na plus ion is 4. And that's why the molecule or the crystal is called 4:8 type arrangement, or simply 4:8 arrangement we have here. Right? Li2O, K2O are this type of structures. Okay.